Hello. A set of billet exhaust manifolds for a V16 Detroit engine. Yeah, we've got you covered. So we need to turn those into those. You feeling confident?
Yeah, I think I can do it.
You got this?
Yeah.
We're going to turn 430 kilos of this into that. You wouldn't want that on your toe, would you? What are you doing today, Nikita?
I'm just machining the manifold.
Nice. All right, Nikita. What are you doing today?
Manifold.
Manifold, nice.
Yeah.
What are you on with today, Nikita?
Manifold.
Right, Nikita. What are you on with today?
Right. Doing a manifold, aren't I?
Yeah.
Yep.
Yep.
Alright.
Manifold, is it?
Yep.
What are you doing today, Nikita?
The manifold.
This is some serious engineering. This is a set of billet manifolds for a V16 Detroit engine. Supercharged, twin turboed, 24 litre and nearly 1,000 horsepower. This is a serious piece of engineering and I'm very proud that it's coming out of my shop. Detroit engines in general are quite interesting. People get quite excited about the sound of a Detroit engine. They sound like they're revving really, really high. It's because the two-stroke, like a four-stroke is doing one combustion every 4 cycles, the two-stroke is doing one combustion every 2 cycles. So when the engine is doing the same RPM as a four-stroke engine, it sounds like it's revving twice as fast because we can hear twice as many combustion cycles. So some people absolutely love the sound of them. Some people absolutely hate the sound of them. I think they're just very interesting engines. They're very interesting also because they have a large supercharger. People get excited about this and they think, ooh, supercharger, horsepower. Well, actually, no. On the Detroit engines, like these, the supercharger is actually designed to help with the induction process. Because it's a two-stroke, it needs help to keep the gas moving in that direction so that we don't basically need a reed valve and the other things that we'd need in a normal two-stroke engine. However, the turbos, they are power adders. So this particular version does get a bump up from the what they would call an NA version, which isn't strictly NA. And this version is closer to 1,000 horsepower. 2,800 pounds-feet of torque, if I remember rightly. The engine that these are going to be bolted to weighs 2.2 tons, 2,200 kilos. In total, there is 8 pieces to this incredible jigsaw puzzle. Costs, because everybody wants to know how much this stuff costs. In material alone, £6,000. What would that be in dollars? 8 grand or something. And 1,000 hours of labour have gone into this. Let's say we were to just charge £100 an hour. £100 an hour to some people in the UK might seem expensive, but if you take your Land Rover Defender or your Range Rover in for a service, in that garage they're going to charge £200 an hour and they're putting an oil filter on. They're not having to make anything, they're not having to put any thought into anything apart from not making a mess or setting fire to the place, and they're charging £200 an hour, right? So imagine if we halved it and we're big CNC machines, serious skill, lots of equipment, knowledge about diesel engines, £100 an hour, that would be £100,000 in just labour. That's not material, you know, any of the consumables or anything else. just labour would be 100,000. So how much did this job cost? Well, I'm not going to tell you, I'm going to leave you guessing at that. I'm going to show you what I mean when I say tooling, high feed. I can show you what some tooling looks like. So when we talk about tooling, this is what I'm talking about. See these little inserts that go in here? They're indexable, they can be rotated, but these obviously wear, especially with stuff like that tough steel, and these might have to be changed. Realistically, what do you reckon, how long?
Half a day.
Oh, it's not
3-4 hours.
3 or 4 hours, and then they have to be rotated.
Yeah.
Yeah. And those things aren't cheap. We're about 6,000 quid into just inserts for tooling. So that doesn't include these holders. But if you were to go out and you wanted to buy one of those machines and buy this equipment and do that, I think one of these now is about 140,000. The XYZ, by the way, just a little bit of information for you. The XYZ, in the UK, it's kind of considered like the sort of Ford Mondeo of CNC machines. It's not like the Rolex, it's not the Rolls Royce. This is like they're heavy-duty machines. It's very, very strong, but not too fancy. It's got the Siemens control, which is the best, but it's not too fancy, so sensibly priced. That one next to it's more expensive because that's a 4th axis, and the one at the end is a smaller one, so that's a bit cheaper. And on one of these tool trolleys, so these are not the tools that are in it, this is a 30 tools in this. So we've got 30 tools in there, and then obviously the ones on the trolley. You've probably got maybe like 15, 20 grand of tooling just for this one machine, and then you've got that for all the others. And then we have a cabinet full of specialist measuring equipment, and that's, you know, that's going to have probably a similar amount again for just measuring specific things, you know, when we're doing like engine work and things like that. These have all got measuring probes on them so they can really accurately measure things, the machines themselves. So that gives you another idea of cost if you thought, oh, I haven't got anything, I want to make that manifold. And that doesn't even account for the time that it takes to get somebody up to that skill level. And then the hypermill program. I think hypermill itself, the cam package, the bit that gets it from the CAD model to the machine, I think that was like 10 grand, and you have to update it every year. That's not cheap. Machining is not cheap. It's really cool, and it's pretty repeatable as long as everything is measured and it's in tolerance. It's pretty repeatable. It is not cheap. Costs. Now, why did we have to make these in the first place? I think it's important to say. Well, the company that contacted us runs this big Detroit engine, and they use it as a pump. And it's very important that this pump works come rain or shine. They started to have issues as this engine's getting older. By the way, these engines are made between 1974 and 1995, so even the newest ones are quite old. And the manifolds, over time, they're very thin, they're thin-walled. They're made out of cast iron. They are not cast steel, cast iron, so a total pain to weld or repair. They warp terribly, and then the flanges and gaskets start leaking. And that's been an issue that they've had with this engine setup, with this V16 Detroit, for many years. And the problem is, we're getting to the point now where a set of manifolds, replacement ones for a Detroit 16 V92, are actually becoming impossible to get. They basically bought the last two. So they needed a replacement. They needed something stronger that wasn't going to warp, that was made of something a bit more ductile, that's going to last a bit longer, that is repairable if needed, and obviously that's available. Not very many companies are going to be willing to do something like this. You've got to imagine this Detroit V16 engine. It's not like a popular tuning engine where it's worthwhile making hundreds of manifolds for. This is very much a bespoke piece. Now, there's not very many shops are interested enough in diesel engines and in engineering that have the ability to actually take this task on. Anyway, so it got passed around a little bit, and eventually it got to us. Kindly, another company passed it on to us, knowing that we had the skills to do it. I dashed off in the van with verniers and measuring equipment to have a look at this engine and see if this project was even feasible. I took loads and loads of measurements of this engine. This was within the second day of being given the job. It's about 300 miles away from our place. Measured absolutely everything, measured it twice, did both sides, and went, right, okay, we've got something to make a design for. We took the old original manifolds, and that's where the designing started, Nikita. He has been working very, very, very hard on these manifolds. So yes, I took the job on and I did a bit of measuring, but I can't take the credit for this. This man here has pretty much been stuck at this for 4 months solid. We've got 3 machines, as you can see in the background. Other machining tasks I have tried to help with. I probably slowed you down more than anything, but the thought was there. But needless to say, we were there, and that's pretty exciting. Been 4 months of machining these manifolds. Do you have anything that you could say that sum this job up?
I knew we were going to be facing with a big challenge. We knew there was going to be a few hurdles along the way. There definitely was, but...
Did you think that my initial time scale of 2 weeks was...
I think we soon found out that
It wasn't, yeah.
it was going to take a little bit longer.
That was a joke, by the way. I didn't say 2 weeks. I think I actually was hoping for like 4 weeks. But after a couple of weeks of actually getting into this job and the sheer size and the weight, just to give you guys an idea, this center section, so this is made up of 8 pieces. We've got 4 base pieces here, which are these collectors. And then we have 2 large, these Y-piece collectors, which connect the front and the rear of the engine together. These Y-pieces came out of a piece of material that was
429.
429 kilos. So the piece of material alone for these was nearly half a ton, which has its own logistical challenges. You know, we're used to making things for smaller engines, 3-litre engines, that even the heaviest stuff, you can lift it in and out of the machine fairly easily. This stuff, obviously, we were going in and out with the forklift. Luckily, we do have access to these machines with forklifts and things like that, so it's not the end of the world, but normally the stuff we're making is, you know, a bit smaller than this. So that was definitely a little challenge, wasn't it? And not only that, you've got to imagine that when you put one of these big pieces of material in, it's not just in until it's finished. I mean, how many ops was these? Were they 4?
Oh, I've lost count along the way machining it.
Probably 4 or 5.
A lot of prep work just to
get it down to size.
Make it, yeah, the size for the vices, to clamp the vices.
Yeah, yeah.
All machining nerdy stuff. But.
Yeah, that was another slight issue that we had. Pieces of material that we had to use ended up being round. The actual stock that we used was basically big, round, cylindrical pieces. Because we couldn't get the pieces we needed in plate soon enough to get this job done. We were definitely against the clock with it. I promised this big company quite a small time scale, and I don't like letting people down. So after 2 weeks of realizing that this project was going to take longer than I thought, I basically fabricated them a set of manifolds. Well, initially I tried to weld these. That's where I realized they're actually cast iron, they're not cast steel. Welding cast iron, I digress slightly for a second because you engineering fans will appreciate this. Welding cast iron is quite a challenge, and you're going to get people commenting online. They're going to say, well, if you use a nickel rod, if you do this, if you do that. The real way to weld cast iron, you can look it up, you can watch videos of it. They put this in a furnace. This is heated up and the whole thing glows orange. Then what they do is they get a little flap and they open the flap and they actually weld while it's still in the furnace. So almost, it's not molten, obviously. You don't want to lose the total shape of it. It will have to be machined. And while it's all orange, basically, they then get a torch and they actually start welding this while it's in the furnace. I don't have a furnace. I don't have the facility to do that. Maybe in the future. I buy a lot of weird things and, well, a lot of machines and equipment. And this is maybe something. But anyway, we couldn't weld it. And neither can you at home, unless you've got a furnace. So don't even start in the comments. I could do it with a brazing rod. There'll be people saying, what's the usual? Nickel, use a nickel rod, use 3. I'm not even going to go into it. They'll be all in the comments. Put in the comments how you would weld that, because I want to have a laugh. Right, we couldn't weld it, we tried. So I fabricated them 2 replacements. I basically got some laser cut flange. This all had to be done very, very fast. Laser cut flange, some box section. It wasn't massively pretty. I TIG welded it, I made a jig to get them going so that you could use like 50% of the cast pieces and then 50% of the pieces I'd fabricated, and they're up and running. As we speak right now, 4 months later, that engine is still running on my fabricated replacements. They're very excited and very keen to get these on there, and so am I. However, there is a couple of challenges we still need to do before they go. So these are made out of EN8 steel. The reason I've chosen EN8 steel is it's quite ductile, welds well if needs to be repaired, because you've got to imagine something like this. Always think for the future, something can go wrong, something can happen, let's make it repairable so it's weldable. But the EN8 will rust. So what you see here is all covered in a special rust guard. All of our steel machined parts that we make get covered in a rust guard spray. It's like a wax, it dries, and it stops them rusting, which is why they look so beautiful now. However, if we were to put those out in the rain or on an engine, you know, they'd be rusty in a few days. You know, they'd start to rust in a few days. That's just the nature of the material, the same as a turbo housing or what have you. You'll be asking, well, why didn't you make them out of stainless? Well, if you thought that this job, you're laughing, if you thought that this job was hard in EN8, a very basic breakdown for people that don't know anything about machining. Aluminium's nice. It means you don't have to change your tools very often, and it's fairly forgiving. Steel is not very nice. It means you have to change your tooling quite often because it wears it out, and accidents do happen. Stainless would be another level above that, where you're changing your tooling almost constantly. Things try to micro-weld together. It's just an absolute nightmare to machine. And like I said before, we needed to keep this achievable, otherwise it wouldn't happen. And the EN8 we use on our billet manifolds, it's very, very good, very fit for purpose. So let's use this. We're good at machining it, it works well. Let's stick to the plan. So, what are we going to do to prevent the rust? These are going to get ceramic coated. Not sure on the colour yet. I'm going to keep that maybe as a little surprise. I might put some photos on my Facebook page, so in the future you might see it. Not quite sure yet. We could go with anything really, but it's going to get a ceramic coating for protection. Also, one thing that we're finishing just at the end of here, look, is the gaskets here at Dieselpumpuk UK, amongst our many, many things. These are the original gaskets that are a composite. They're like a fibrous, and they have a steel inner ring to protect them. Basically, fibrous gaskets like this are good for uneven surfaces. So if you've got two things and it's slightly warped or it's a bit of a problem, these are pretty good because they're soft. Imagine it being like a big bed mattress and it'll squeeze easily and it'll go around. Basically, if you're bodging, these are great. However, as you might have gathered from this video and the 1,000 hours of work we've put in, our intention is not to bodge. So what we have done is pressed some stainless steel gaskets. Now basically what we do is we get a laser cut or a water jet shape, and then we make a tool that allows us to press a ridge-in. And these can be stacked for multiple layers in certain applications, just like a multi-layer steel head gasket. So that is for the big one, and this is for the smaller ones at the bottom. Now this, you'll notice, is a different material. This is for the cylinder head to collector, and you'll notice it's copper. I really like using copper as a gasket material between cylinder head and exhaust manifolds. Now, copper's not really suitable for further upstream in the exhaust system because it can't take the heat. However, where it's fastened directly to the cylinder head, which is water cooled, it works absolutely brilliantly because it allows the temperature to conduct really nicely between the head and the manifold. So the warm up and cool down process between the two is really good, and it's coolant temperature stuff. We're around 100 degrees, which is fantastic for copper gaskets. So one of the gaskets that was leaking quite regularly on the cast versions was this one just here. Have a look at this, come close in. So what we've done is, look at that. We've made a receiver groove. So not only will we have our stainless gasket going around here, but we've also created this like fire ring towards the top. So this will help to locate it. Look at that. Oh, just the way it clicks in. Let's just do that again. You ready? Flawless. I love that. I love that. Almost like a combustion guard, really, to stop the gases being able to fly out of the gasket like they have been. There's no point us doing that to this top side where the T6 because the turbo won't have the receiver. Can we have a minute for Nikita's hard work? 4 months, 1,000 hours. I think that's some good shit. Well done, Nikita.
Thank you.